Why waste time in commute and spend lot of money for iitjee coaching? Parents, do you want your kids to achieve top scores in iitjee? India's leading online NEET coaching 100% success iitjee. At TeenEinstein, we focus on iitjee coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com.
Let us start Quantic Theory of gases. So everything around us is made up of matter, and matter is made up of atoms. Now, atom was considered to be the most fundamental particle, but now we know that atom is further consists of a nucleus, which further consists of protons and neutrons, which further consists of quarks and strings. But for now, let us come back to our atom. So the size of an atom is around 1 angstrom, that is 10 power minus 10 meters. Now, matter is something that occupies a space, and it exists in three states, that is solid, liquid, and gas. How can we differentiate between these states? Based on our observation. They have different intrinsic properties based on the arrangement of atoms within their structure. That is, in case of solids, you can see that atoms are tightly packed. They are not free to move. There are strong intermolecular forces. In case of liquids, they are loosely packed. That is why a liquid is able to flow, and it can get stored in any container and take the shape of the container in whichever you pour it in. For the gases, the molecules are far apart from each other. They don't have either any shape, the gas doesn't have any shape or any fixed volume, and the molecules are free to move. So, what is the nature of intermolecular forces? So, if two atoms are brought close to each other, they experience a bit of repulsion. So, its nature is short range repulsion. And if two atoms are at very far distance apart from each other, they experience attraction. So, solids and liquids have a long range attraction and short range repulsion. In the case of gases, as you know that the molecules are not bound, so they are in dynamic equilibrium. That is, the gas molecules, since they are free to move, they keep on colliding. And at each collision, they change their speed, direction, change their momenta, exchange energy. So only average properties of gas are constant. Now, what does kinetic theory tell us about? Kinetic theory explains the behavior of gases. It was developed by Maxwell and Boltzmann in the 19th century and explains several properties of gases like specific heat capacities, viscosity, conduction, and is consistent with the gas laws. It also gives a molecular interpretation of pressure and temperature of a gas. So now let us study mean free path. So consider if you keep a gas enclosed in a container. So you can see that the gas molecules are free to move in random directions. Now, if one molecule strikes with another, so the distance a molecule travels without colliding, that is, this distance, is known as free path. Now, this can undergo collision with this, which can further undergo collision with this, and this can take place so on. Collisions can take place randomly and so on. So the average distance, if you find out this average distance of the molecules, this is known as mean free path. The order of mean free path in gases is around thousands of angstrom. Now let us study behavior of gases. Gases satisfy a simple relation between their temperature, pressure, and volume, which can be seen by equation 1. That is, the product of pressure and volume is equal to K times the temperature of the gas. Here, K is a constant, which is for a given volume of gas, and it is proportional to the number of molecules, say N. So let us write a small k as a product of number of molecules and another constant known as Boltzmann constant. Now consider two different gases. One gas having pressure P1, volume V1, temperature T1, and number of molecules as N1, while the another gas having pressure P2, volume V2, temperature T2, and number of molecules as N2. Then, using equation 1, can we derive a relation between them? Yes, and this is that relation. What we can observe from this relation is that if two gases have same pressure, same volume, and same temperature, then the number of molecules between these two gases is the same. This was said by Avogadro, and this is known as Avogadro's hypothesis. So Avogadro's hypothesis states that that the number of molecules per unit volume is same for all gases at a fixed temperature and pressure. Avogadro's law also said that molecules in 22.4 liters of gas, any gas, the number of molecules is 6.02 into 10 to the power 23. This is known as Avogadro number and is denoted by Na. Also, we can define 1 mole using this, that as the mass of 22.4 liters of any gas is equal to its molecular weight in grams at STP. What is STP? It is standard pressure and temperature. Standard temperature is 273 Kelvin and standard pressure is 1 atmosphere. So we can write PV is equal to mu RT. Here mu is the number of moles and R is the product of Avogadro's number and Boltzmann constant. So any gas that satisfies the above equation is known as an ideal gas. And it is a very important property of gases that they behave as ideal gas only at low pressure and high temperatures. That is, the moment the pressure becomes high and the temperature becomes low, there's deviation of the gas from its ideal behavior. That we'll see from Boyle's law. So now let us study Boyle's law. If we consider temperature to be constant, we can get PV, that is pressure and volume, as a constant. That is, we can obtain an inverse relation between pressure and volume. So this, let us consider the plot for Boyle's law. Here on the x-axis we have volume and on the y-axis we have pressure. And the data is for three temperatures, at three temperatures, T1, T2 and T3. T1 is the highest temperature, T3 is the lowest temperature. These dotted lines represent the theoretical prediction obtained from the Boyle's law, and the solid lines represent experimental data. So we see that at very high temperature, that is T1, which is the highest temperature, there is some agreement between between experiment and data. And we can see that at low pressure, around 0.4, the experiment and data almost matches. That is, experimental data and theoretical prediction matches. Now, as we decrease the temperature, that is, now we come to a lower temperature. This is T2, which is from the law. And here we see another T2, that is the solid line, which is from the experimental data. Here we see that a lot of deviation is there. That the deviation, the experimental data is deviated from the ideal behavior. And we can see that only at low pressure, that is between 0.2 to 0.4, there is some agreement between theoretical prediction and experimental data. Now you come over to the lower temperature, that is the lowest temperature, T3. Here this is T3, this is again from the law, and this is the experiment. Here we can see the deviation has increased, and only at very low pressure, that is around 0.1, there is some agreement between theory and prediction. So this was Boyle's law, which states that the pressure and volume of a gas are inversely proportional to each other if we keep temperature constant. Now moving to the next law, that is Charles' law. Now if we consider pressure to be constant, so we will get a direct relation between volume and temperature, that is, they will be directly proportional. Again, consider this plot between volume and temperature, and at three different pressures. Pressure P1 is the highest and P3 is the lowest. So here we can see that at high pressure there is a deviation, and at low temperature we can see a lot of deviation. Only at high temperature, that is, as the temperature is increasing, there is some agreement between theory and prediction. Now we lower the pressure. Here we can see that there is some agreement, but still at very low temperature, there is a lot of deviation. And at even lower pressure, again we can see that at very, very low temperature, there is a lot of deviation. So Charles' law states that the volume and absolute temperature of a gas are directly proportional to each other if we keep the pressure constant.
Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry and biology for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com. Contact 99402 49720.